Okay, so I'm very happy to share with you what I've been up to, Ron and I have been up to in the past couple of years. And our topic of research is zero knowledge in streaming interactive proofs. So if that doesn't mean anything to you, hopefully in a few slides it will. Okay, so let's start with some motivating example. So take a look at this grid. Observe this animation, the following animation, and I will ask you a question about it. Okay, now the question is, was the dotted spot blue? Anybody know? Okay, well, I'm going to prove to you that it was. Okay, here's my proof. Ta-da! Well, now, so hopefully, during my time at the Technion, I've established myself as a trustworthy person, so you won't think I'm lying to you. But also, hopefully, you think that this is not a very convincing proof, just showing you that it was. So in this talk, I'm going to show you how I can prove to you that it was blue. In fact, it wasn't, by the way. Or that if I'm lying to you, then you will be able to catch me with high probability. But at the same time, I can do it in a way, if the claim is true, that will not reveal much more than just saying ta-da. Okay. So our main framework is called interactive proofs, and this is has been studied since the late 80s, attributed to Goldwasser, Mikhal, and Rakov. And in this setting, we have a prover and a verifier. And the prover wants to prove to the verifier that some claim is true. In this case, we know it as X belongs to some language F. And in order to do that, they can interact. So they can send each other messages, ask questions and answers. And at the end, the verifier needs to decide whether to accept the claim as true or to reject. Now, what we want from this is the following properties. First, we call it completeness, which means that if the claim is indeed true, then we want the prover to be able to convince the verifier to accept as a true claim. And soundness, it means that if the claim is not true, then it doesn't matter how powerful or devious the prover might be in trying to convince the verifier to accept, it will fail with high probability. And another interesting property of interactive proofs that we can ask for is what we call zero knowledge, which at least intuitively means that after the interaction, the verifier has not learned anything except being convinced that the claim is true. Okay, now if you take this very stupid example that I have here on the screen, this proof system is not sound, because if a verifier accepts after these unconvincing claims, then it would be very easy to fool. But it is, in fact, zero knowledge, because at least intuitively, the verifier could have had this whole conversation in his head, didn't need some powerful prover to tell him these things. So we might think that there is some inherent trade-off between soundness and zero knowledge, and the surprising fact is that, in fact, those two can coexist. Okay. So we go into kind of a sub-subject in interactive proofs, and which is called streaming interactive proofs. It started becoming popular in the previous decade, and it's not a surprise since we started all these algorithms that work on huge swaths of data, like training neural networks and all that. And in streaming interactive proofs, the setting is similar. We also have a prover and a verifier. But the difference here is that the input to the problem is huge. Okay? So our prover, we assume it to be unbounded, so it has a lot of storage space. And the verifier is bounded, and it's mostly bounded in storage, so has small memory. So it's so small that it cannot contain the entire input. So in order to read the input, they stream it at the same time. I read it bit by bit. And as you can see, the prover can store the entire input, and the verifier can remember something from the input, but most of the information is lost. Okay, so and then they do the same, they can interact, and then at the end, the verifier needs to accept or reject if the claim is true or reject if it's false. Okay, so just a little bit more in detail, we assume that the space of the verifier, denoted here by SV, is much smaller than the input length, polylog in the input length, and denotes here the input length. We want the messages between the prover and the verifier, the communication complexity also to be short, so polylogarithmic in n as well, even though sometimes it could be more. But even if it's polylogarithmic, it can be a bigger polylog than the verifier space. So the prover can send his messages also by a stream, and they stream each other the messages. And even though what we're mostly concerned about here are the space limitations, but also we want for everything to run efficiently in time. Okay. So about 2 years ago, when I came to Ron's office and we started thinking, what should we do? Cormod, Dalamiol, Gur, and Hickey just published their paper asking the question, what the hell is zero knowledge in the streaming model? And we looked at that paper and thought, well, maybe we can do something, improve on that. So now I'm going to show you our definition, which is slightly different, but morally the same as theirs. The following is only for intimidation purposes. Please do not try and read it. Okay? So I'll put it aside and I'll explain what we mean in an intuitive way that's not as intimidating as this.
That's a question
Yes.
about the basic model even. Is it known to the prover what the verifier keeps in his memory?
No.
It's randomized?
Yes. Verifier is randomized.
And the verifier knows which statement it will want to verify later? Because like in your example, is this blue dot? If we knew that you are going to.
So I will talk about this. No.
Wait to see.
I will talk about specifically about that example, but yes, the question which dot it needs to verify comes only after, like exactly like in the example I showed you. But I will talk more specifically about that later. But yes, great questions.
And also, why do you insist with the communications polyalgorithm?
So it's not going to be, but we want it to be because in the streaming setting, if you have linear communication, then sometimes it can make some problems much easier, almost trivial. So not, well, depends how you define trivial, but it's nicer when you also keep the communication complexity to a minimum. In one of our protocols, unfortunately, we weren't able to achieve that, and I will talk about that later. Okay, so we have this denotes the real protocol between the prover and the verifier, and you have the asterisk here to denote that the verifier might be malicious. It might want to learn something that it's not supposed to from the prover. And their input is X, which they stream in the beginning. Now you can think that there is someone at the entry gates of the verifier, and everything that he sees during the protocol in the order that it sees it, writes it down. So, and we call this the verifier's view, and this can consist of bits of the input, of the randomness of the verifier, and the prover messages. This is basically everything the verifier sees during the interaction with the prover on the input X. So everything that the verifier can learn comes from the verifier's view. So we say that the verifier didn't learn anything if the verifier could somehow simulate this view without the help of the prover by itself. So we say that it's zero knowledge if we can construct a simulator which only takes X as an input without the help of the verifier, that can produce a similar string, and what do I mean by similar? So they're not going to be exactly the same, but they need to be similar enough such that there is another Turing machine, which is small space and streaming, such that if we give one of those as a stream to this distinguisher, and we ask it, where did it come from? Did it come from the real view or the simulated view? Then it will not know. Or, I mean, the distinguisher can always, with probability half, guess. And we say that the protocol has error delta if any distinguisher with a streaming small space Turing machine cannot distinguish with probability more than half plus delta. Okay, so just to forget about all these markings, if, for example, you didn't come to this lecture and somebody asked you, hey, what did Tomo talk about? And you were able to convince them in a way that you did come to this lecture, then it probably means I didn't teach you anything here. Okay, great. Okay, so that's our definition of zero knowledge. And the last thing I need to tell you before we actually start is the main problem that we're dealing with in this talk mostly is called the polynomial evaluation problem. And it's a very well-named problem. The input to the problem is a polynomial. We can, for simplicity, think of it as a multilinear polynomial, represented as a list of evaluations in the n-dimensional Boolean hypercube, but you can just think of it as just represented efficiently. And then a point x and a value alpha. And what we need is to accept if the value of the polynomial at point x is equal to alpha, or reject otherwise. Okay? So I hope that kind of reminds you of that little experiment I did in the beginning. And now, Hagit, to your question, first of all, we note that this problem is hard for a small space streaming algorithm. Yes, so as you noticed, you saw all the colors, but you weren't able to remember all of them. And then when I asked you about a specific one, you didn't remember. So, I mean, you can guess yes or no, and then get a probability 1/2. And this term is kind of says that you can guess in the beginning which colors, which points to look at, and hopefully one of them is going to be the one that you're going to be asked about. And what you said is the input of the order of the input is extremely crucial, because if I first ask you, well, I'm going to ask you about this dot, and then stream the dots, then obviously that would not be a problem for you to tell me if it's blue or not. Okay, great. So just a little of summary of previous results before us. So Kormo et al. In 2012 show streaming interactive proof, which is, we don't talk about zero knowledge, for general computations. They show streaming interactive proof for the GKI protocol, if anybody knows it, and which covers a lot of a large class of languages. And then in 19, they show a specific, very efficient streaming interactive proof for the PEP problem that I just showed you. And we're going to look at this protocol carefully. And then 2 years ago, Kormo et al., it's the same C always, gave us the definition, offered a definition for zero knowledge streaming interactive proofs, and showed a protocol for PEP, soundcheck, and several other main problems in the streaming literature. Okay. Now I'm gonna show off what we did. So our main result is to give the first general purpose zero knowledge streaming interactive proof for a very large class of languages. So that class is all languages in NP. that have a relation decidable by polynomial size, polylogarithmic depth family of circuits. So it's not all of NP, but some of it, or a large part, an important large part of it. So we show that those languages have streaming interactive proof with negligible soundness error and polylogarithmic honest verified space. Now here, as I mentioned, the communication complexity is polynomial, which is something that hopefully in the future we can improve on. And there is a almost nearly quadratic gap between the space that the honest verifier needs to have in order to execute the protocol, and that what we are zero knowledge against adversaries with against verifiers with space quadratic in the honest verifier. And we get also a negligible zero knowledge error. And as a bonus, also the prover is efficient, which is, again, we don't care as much, but it's always nice to get efficient algorithms. So this is our main result. And in order to get there, we first show streaming zero knowledge interactive proof specifically for the PEP problem. And now a little comparison between our work and the protocol of Korban et al. So we have both a polylogarithmic space of the honest verifier. Our communication complexity is polylogarithmic while there is superlinear. We get perfect completeness and negligible soundness and negligible zero knowledge error, while they have errors that are only sub-constant. We get a gap between the honest verifier and the malicious verifier, well, they don't have, but the only downside of ours and what they do better is that they can fool more powerful distinguishers. Again, something to improve on. Okay, and the last thing, and this is basically the main technical thing that we offer here in order to construct the first two, is two new streaming commitment schemes. Okay. Questions? Great. So now we can start to talk. I will show you a little bit about our construction. So I'll start with the streaming interactive proof for the PEP. Start with the non-zero knowledge version of CCM 19. Show how we make it zero knowledge using streaming commitments, and then construct the simulator, which hopefully will convince you that indeed it is zero knowledge. Then I'll show you the streaming commitment schemes that we constructed in order to put them inside our protocols. I made the presentation, I was going to present both of them, but then I realized that it's going to take way too long. So I'm going to stick to the first, which is the simpler one. If anybody's interested in the other one, I'll be happy to tell you about it. And lastly, I'll show you in very broad strokes how we get to our main results using everything we did before. And we basically construct a compiler from a different model to the model that we need. Okay, so let's start with
Both are going to commit,
what? Yes, we have two commitments.
so that's why you need to.
Yes.
Okay.
Okay, so before we start with this, I'm gonna take a sip of water. Okay, and now the fun part. Okay, so let's go back to our example. What? Not Pepsi, no. I don't like it as much. Okay. Great. So let's go back to our experience from before. So hopefully you don't remember what point I asked you about. So also now you can't tell. And I will ask you, what's the dot in this spot blue? Or if we're talking about polynomials, is the value of the polynomial at this point 17, for example? Okay. And we said that if I just tell you, yes, it's 17, then it's not convincing. So what we can do is, okay, don't show me just the value there, show me the entire thing again, and then I'll see whether it's consistent or not. So I'll say, okay, fine, I'll show you the entire thing again, and now you know where you need to look. So you see the entire thing again. You see that indeed it is blue, but again, hopefully that's not convincing because I could send everything the same, but change just that dot and again lie to you. So how would we solve that? Look outside the box. So let's keep the inputs here, even though we imagine that we don't have enough memory for that. And we define colors for points outside of the input square. How shall we define it? So let's look, for example, at this dot. The color here would be some linear function of all the colors of the input square. So this would define some set of coefficients where you multiply them together and add up to get some color. Yeah, so every different dot would have a different set of coefficients, which would result in a different color. And ultimately, every point on the grid is defined with some color. Now, if, for example, I take this and I change this color, then this would affect almost all other colors. So what we can do now is the following. Let's think we're restarting the protocol again. Before you look at the input, you pick a random spot, which I, as the prover, I don't know. I can't know it, because if I know it, I'll be able to do some nasty things. Which, as you remember, defines some set of coefficients. Now, you have small space, so you can't remember all these coefficients, but you can compute each coefficient when you need it in small space. Okay, so now we stream the input together, and you compute the coefficient, multiply it together, and then you can compute what we call the input signature in small space, no problem. And I don't know what that is, what you chose. So that's the input signature.
In a sense, it's some sophisticated.
It's a hash.
Sum that you compute on the inputs.
Yeah, it's just a hash. I'm showing it like this so we can develop it later. Great. Now I ask you, was the dot in this spot blue? You say, okay, dear prover, please send it again. And I said, fine, I'll send it again. Again, you have your coefficients. I send you what I claim to have been the input. You see that indeed the dot here is blue, but now the signature is different. So you know that I lied to you. And you caught me. Okay. Now this is great. This works. This has completeness and soundness, but the problem here is that the communication complexity is very large. I, as the prover, have to send you the entire inputs again, and we want to do it in some logarithmic communication complexity, not linear. So let's see how we solve it. So to solve it, we're going to use a much smaller, more modest input of only 9 dots. Okay, and let's just keep him on the screen because, but we assume that the verifier cannot remember these 9 dots. Okay, so as we said, these are not actually, they're not colors, they're values of a polynomial. So we'll just look at it like that. And since discrete polynomials are ugly, even though we are in the computer science department, we'll fill in the gaps for it to look nice and smooth. So again, we look beyond the input square. And this polynomial is well defined also outside. And also, like in the 2D example, every point here in the space is a linear function of these 9 points of the input. So you, as the verifier, again, pick a random point, let's call it this, and as the input streams, you can compute that point, the value of that point, in small space. Now comes the part that you're asked, what is the value of the polynomial at this point? And this is the part where we need to solve. We don't want the prover to send the entire polynomial again. So what do? Let's look at the input domain, the inputs of the polynomial, right? you stretch a line between your point where you computed the signature and the point that you're interested in verifying. Okay? Now, and you send this line to me, to the prover. Now, recall that me as the prover, I can't know. If I know where you computed your signature, then I'll be able to cheat. So you're giving me some information about where the signature might be, but still the line is very big. We're working over a large field. So still there's a lot of uncertainty for me as a prover where your signature is. And now notice this line is kind of like a big knife that cuts the polynomial. So if we look at it from another angle, this actually, we get a one-dimensional polynomial that also passes through the point that we want to verify and the signature. But this polynomial, being one-dimensional, can be represented using only 5 points. So now the prover can send those 5 points instead of the whole 9 points of the original input. And notice that here also, if the prover cheats and sends different points, then the polynomial is not going to match the signature with high probability. So we can catch it again. Okay, so now 5 points might not sound a lot less than 9, but it's actually going to be with the right parameters, sending log of n instead of n, which saves a lot. Okay. Any questions about that? Okay, I'm going to take another sip of water. Great. So now let's lay this protocol out on a boring 2D surface. So we have our prover and verifier. So the verifier chooses randomly a point in the polynomial, in the domain of the polynomial. Then they stream the input. The prover stores everything because it can, and the verifier stores that point, the evaluation of the polynomial at that point, x and alpha. Then constructs the line, we call it L. Don't worry about this mu, that's just to shuffle the points that the line is on. So the prover can't tell R from L. And then sends the prover the line. The prover then constructs G, that's the one-dimensional polynomial. Sends that to the verifier, and then the verifier can verify both the points that it needs to. Okay, so this is a very nice protocol, but it is non-zero knowledge. And the reason it's not zero knowledge, at least intuitively, there are 2 places where it's not. So firstly, let's say we even have an honest verifier that doesn't even want to learn anything, but still, when the prover sends G, then G contains more information about the input than we want to give to the verifier. Yes, because G contains all the values of the polynomial P on a line that passes through X. Now, this is not something that the verifier could have come up by himself. So it gets some knowledge about the input. And the other thing is that, let's say the verifier is not honest, and the verifier can send a line. After it saw what the point X is, it can decide what line to send, which doesn't necessarily have to coincide with the point that he chose before. Okay? So, how do we circumvent this? Using commitments. And since I don't know if everybody here is sharp on their commitments, then just a very short slide about what are commitments. So commitment schemes are protocol between 2 parties, here demonstrated by my 2 cats, where there are 2 phases. In the first phase, the sender has a message that he wants to send to the receiver. So he locks it in a box and sends the locked box to the receiver. And then the second phase, the sender, it's called the decommitment phase or the reveal phase. The sender sends the key to open the box, and then the receiver can see what was inside the box. Okay, we want 3 very natural things from this thing. First, correctness means that if everybody is honest, then the message that the sender sent would be the message that the receiver got. Hiding which means that before the receiver gets the key, he has absolutely no idea what's the message that's hiding inside the box. And binding means bli charatot. Once the sender sent the locked box message, the message in the locked box, even if it really wants to, that's it. It can't open the box to a different message. Okay, that's very natural idea, and hopefully that's clear. So let's go back to the protocol and see how we use commitments in order to make this zero knowledge. Okay, so first of all, the verifier is going to send a commitment to its secret randomness R. Okay, now since the commitment is hiding, then the prover still holds the commitment, but it can't see what it is. Okay. Now the second commitment is going to be here. So instead of sending G in the clear, the prover is going to send a commitment to G. So the verifier at this point doesn't know what G is. And the commitment that the prover sends is what we call a polynomial commitment, which means that he can open it to only specific values in the polynomial without revealing what the other values on the polynomial are. Great, so, well, now we can't really do this check, so we have to move it a little further. At this point, the verifier will send the key to its commitment. The prover can then see what R is, and now we can check that indeed the line L is indeed a line that connects X and R, and that the verifier did not send some other L which is correlated with X. Because remember, R was chosen before it saw X. Okay? And now, after it verified that indeed L is the line that connects X and R, it will send in the key to open exactly to just the 2 points, if you remember the red dot and the orange dot, without showing anything else. So we're fine with this, and we're fine with that. And this protocol is hopefully, at least intuitively, zero knowledge. And it also satisfies completeness, because if the commitments are correct, then if everybody's honest, nothing gets messed up and the verifier will accept. And the soundness relies, well, on the soundness of the protocol, of the non-zero knowledge protocol, together with the fact that this commitment is hiding. So up to the point where the prover sends the commitment to G, he has no idea what R is. And after he sees what R is, he already committed to G, so he can't change the values. Okay, so great. So now, in order to actually argue that this protocol is zero knowledge, if you remember that by the definition, we have to show a simulator that simulates the view of the verifier during the protocol.
What is zero knowledge? What's the error probability? You cannot repeat this, right? With the same.
Yeah. So it's negligible. So if you take a large enough field, then you get the error probability. The soundness error is negligible, and also with the right parameters of the commitments of our commitments, we also get negligible soundness error.
I think you meant negligible zero knowledge error at the end.
The zero knowledge error is
Was it?
What's that?
I thought you meant like both soundness and zero knowledge error, but maybe I missed the question.
Yeah, the zero knowledge error is also going to be negligible, but I guess I haven't gotten there yet. Okay, so we need to construct a simulator, which will replicate the view of the verifier, everything that the verifier sees. Now, the big problem here is that note that the verifier sees the point G of mu, which needs to be P of R. Now, a prover that can store all of the inputs, all of the polynomial, when it gets L, it can, well, construct G, which contains this point, which is the correct point. But a simulator needs to have about the same space as the verifier, and it cannot store all the polynomial. So by the time the simulator sees the line L, it doesn't it can't know what the point P of R is going to be, which is a big problem. Therefore, we kind of need to give the simulator an extra oomph for it to be able to do what it needs to do. And basically what we needed to do is to be able to break the commitment of the verifier. So at this point, when the verifier sends the commitment to R, the simulator needs to be able to break it. So we ask ourselves, what advantage does the simulator have over the prover? The prover is unbounded. The simulator needs to be space bounded like the verifier. So the biggest advantage is that the simulator contains the code of the verifier and also can set its randomness to get the result that it needs. Another advantage that also is common in the non-streaming zero knowledge literature is allowing the simulator to rewind the simulation. So basically, he tries to simulate, and then if he fails, then it's like, okay, well, let's try again. And we want it not to fail with high probability, but let's leave that. The problem with the streaming model is that you can't rewind. The whole point of the streaming model is that the input is streamed once, and if you stream it more than once, then I mean the whole problem becomes there's nothing to talk about. So in order to circumvent that, in our model, we allow the simulator to be a read once branching program. Now, I made a whole slide about what the read once branching program is, but unfortunately there's no time. So I'm just going to say that it's a non-uniform model of computation, but it's well studied. And it basically captures the limitations that a small space streaming Turing machine has, but it can also has that extra oomph that we need, and I'll in a moment talk about what it is. So we show that the read once branching program simulator can actually break the hiding of the commitment and then get the value R before the input stream and thus compute P of R. Okay, so just a few words about how it breaks the hiding of the commitment. So as I said, the simulator is specifically tailored to the verifier, whereas the prover is general. So that gives him that edge that it needs. And also, read once branching program, the little extra oomph that it has is that if there's a function that's independent of the input, it can compute it. Even if it's an uncomputable function, it can immediately just get the answer to that function. Now notice that the commitment to R happens before the streaming of the input. So the commitment to R is independent of the input. And if so, it's enough to show that there exists a well-defined function mapping the commitment, or more accurately, the state of the verifier after it committed to R to that R, to the committed value. And now, intuitively, why this function exists is because of the binding of the commitment. So even a malicious verifier can't really do whatever it wants after it committed to a particular value. Okay, now, this is kind of the most delicate and complicated and long proof of the entire paper. Unfortunately, I can't really go into much more depth than this. Hopefully, this makes sense and you're not getting the feeling that, well, we just cheat and get the value and everything's okay. Okay, so given the fact that the simulator has the ability to extract the value of R, this slide, I'm gonna go by quickly because I want to go to the next thing, to have time to go to the next thing. But basically, I show how every step of the real protocol, the simulator can simulate that. And the most interesting thing here is that note that the prover constructs the polynomial G, but the simulator, well, it knows the two important points, which is alpha and P of R, but all the other points on that polynomial, it has no idea what it is. But the nice thing is it doesn't need to, because what the verifier sees is a polynomial commitment to G, and the reveal is only for those two specific values. So even though the simulator commits to a different function, G prime, which is not equal to G with very high probability, the verifier only sees those values from G prime, which are consistent with G. Okay, so hopefully that convinced you that indeed we constructed the simulator properly and that the proof is zero knowledge indeed. So now I want to spend a few minutes on showing you one of the streaming commitments that we constructed, and that's going to be the commitment that the verifier uses in order to commit to the value of R in the beginning of the protocol. Okay, now it's a statistically hiding streaming commitment, and once I take a sip, I will tell you what that means. Okay, so what's statistical hiding? Means that every two possible messages, then the boxes that lock them look the same, basically, or almost entirely the same. And it doesn't have to do anything with the computational power of the adversary trying to break them. So that's basically what it says. And the commitment is going to be computationally binding, which means that it's binding, but only to small space streaming machines. So basically what this is saying, that any small space algorithm cannot produce a box and two different keys such that one key opens the box to one message and the other key opens the box to a different message. Okay, now the cool thing about this model and about the computational binding, that is in fact information theoretic. So it doesn't require any computational assumptions like in the kind of the standard cryptography that we know. We don't need P to be not equal to NP. We don't need one-way functions, any of that.
It's used by the prover.
This is from the verifier to the prover. So the prover is unbounded, so it needs to be statistically hiding.
Said that you could compute a function from the commitment to the message. And here, it's like you cannot do that, right?
The statistical hiding part.
Yeah.
So yes, I mean the proof that a read-once branching program can basically break the hiding is based on the fact that the simulator has simulation access to the verifier. And again, I don't think
It's not like a black box to verify. It actually looks inside.
well, because it's a branching program, then I guess the states of the verifier actually are also the states of the simulator. They're inside there. So yes, it is kind of a little bit of a cheat, but not too much, hopefully. Okay, so here's
I disagree about the cheat. I think it's fine.
okay, yes.
But maybe to clarify the point, you said that we need the extra oomph. The cheating prover has the same oomph, but the fact that that's just like translating what you said. The fact that the simulator can break it is the combination of the oomph plus having direct access sort of to the verifier.
Okay. Yes, it's kind of a delicate point and probably needs more than kind of an overview. Okay, so we have I want to show you the construction of the hiding streaming commitment. Here we have a sender who has a bit that it wants to send. It's going to be a bit commitment, so the sender has either a 0 or a 1, wants to commit to that bit to the receiver. Lambda here is a security parameter. Okay, so first the sender draws randomly 2 vectors of length 4 lambda, binary vectors. And then the receiver randomly draws a matrix, binary matrix of size 4 lambda over lambda. And then first the receiver, by way of streaming, sends A row by row to the sender. And as it streams the rows of A, it computes a value which we call alpha, which is S transpose times A. Okay, now if you're wondering how it does that when A is streaming, when the receiver is streaming A row by row, it can compute it like this in small space, no problem. Okay, now the sender computes the value beta, which is the inner product of S and R, XORed with the value that it wants to commit to. And the commitment is just R, alpha, and beta. Okay, then in order to decommit, to show what the bit B is, simply sends S. Then the receiver verifies that indeed S transpose A is equal to alpha, and can compute the value B by simply XORing the inner product of S and R, which it now has, with beta. Okay, now let's see that it is indeed hiding and binding. So why is it hiding? Note that all that's missing at this point, this is the locked box. All that it needs in order to open the box is S. Now, some of the information about S is in alpha, because alpha is equal to S transpose A. Okay? But the point is that there is not enough information in alpha in order to be informative enough about the key. Yes, because alpha is only lambda bits long. The key is 4 lambda bits long, so there are 3 lambda bits that are lost. So then we invoke the leftover hash lemma, which is very common to use in cryptography, and we show that indeed this looks exactly like just a random bit, basically. Okay, so that's why it's hiding. And why it's binding is this is the test that it needs to pass in order to decommit to a different bit that then S would have to send, well, the sender would have to send a different S that also passes S. Yes, so S prime that is not equal to S such that this equation holds. And rewritten, it means that it has to find a vector, and a non-trivial vector in the kernel of A. Okay, now we use a very, very beautiful theorem by Ilan Raz that basically saying that if you want to solve a set of lambda linear equations over lambda variables, you basically need to store the lambda equations to have space lambda squared. And if you don't have that, you don't have any chance to solve that equation. And what we mostly show, the main technical part of this proof, is showing a reduction from solving equation to finding a vector in the kernel. So we show that if you find a vector in the kernel, then you are able to solve equations, and then by that contradicting the theorem of Raz. And so our sender needs space O of lambda to execute, but it cannot have space, that needs to have space less than lambda squared in order for this to be secure. Okay, the last little thing that I'll just kind of go by quickly is that note that we need to simulate this thing. This is a part of the protocol. And in order to show that the protocol is zero knowledge, this needs to be simulatable in small space, in the space of the sender. So in order to simulate it, or in order to execute it as it is now, the receiver needs to store all of A, which is O of lambda squared. So the simulator that has only a space approximately lambda cannot do that. So in order to circumvent that, we use a trick. We have the receiver draw a random matrix which is much smaller, and then as it streams the rows of A, it doesn't store A, it stores AT, which is much smaller, and it can store that, and then it can check, do this check instead, and the hiding, the binding, and the correctness remains as it is. Okay. So now, just the last part, I'm going to show you very briefly how we got from everything we saw before to our main result. So we are considering another model called IPCP, whose study began in 2008 by Kalai and Raz, the same Raz from before. And basically in this model, again, we have a prover and a verifier. The prover wants to prove some claim to the verifier. And before they start interacting, the prover sends some long message, not directly to the verifier, but I guess up in the air, in a way that the verifier has query access to that long message. So then they can interact. And then before the verifier makes its decision, it can query some bits from that long string, take that into consideration, and then decide whether to accept or reject it. Okay, so we find this model pretty close, in a way, to the streaming model. So we construct a compiler that takes an IPCP and turns it into a streaming interactive proof. And the way we do it, again, in really broad strokes, and in a way that reminds us of what we did in the PET protocol, the verifier first commits to its randomness with a streaming with a streaming commitment. Then the prover commits as a stream to the PCP, this long string, and then at the end, the queries are simulated by the verifier decommitting to its randomness, and then the prover decommitting to the relevant bits of the PCP. Okay, and then we just take kind of an out-of-the-box zero-knowledge IPCP for low-depth relation from Chiesa et al., pass it through our simulator, which we show maintains zero knowledge, and we get our result. Okay, so we made it through. Just to summarize, so we offered a refined definition of zero knowledge in the streaming interactive proof model. We show how to get a better streaming interactive proof for PET using our new streaming commitments. And then we get from that to a general purpose streaming zero knowledge proof. What is left to do, some open questions, is first, the thing that's most poking me in the eye is the whole non-uniformity of the simulator. And it would be nice to get the thing in a completely uniform setting. And the other thing is that we need to have a polynomial communication complexity in that main result that we have. And if we can get a better communication complexity, that would be great. And if the answer to these two questions are no, then to show that it's something inherent to the model and not our lack of ability to show that a better solution. And yeah, that's it. Any questions? Usually there aren't any questions, but
The previous PET We use.
Yes,
commitment,
they use commitments, but
But
not-
your advantage was better commitment.
yes, but yeah, the main thing is better commitments and more refined definition.
And if you could,
Or exists the definition.
Or what?
Exists the definition.
I need to start bothering us. If you use the previous commitments for the NP protocol, you could not do that.
But you would get much worse parameters. You could potentially get that. I didn't
didn't
check.
try.
I didn't try. But anyway, the parameters can be much worse.
And can you give examples of NP languages that have low depth? Maybe a YAL can, if you can.
So
A lot of them, no?
Let me change the question. Can you give an example of a language that does not have low depth? Oh, so like, what's your favorite NP problem?
Oh, they are continuing to saying nasty things about you instead of
Okay. Bye.
Okay, so I just want to spend another minute to thank Ron. This really has been a very interesting little journey, and any superlative that I would say would not describe fully how wonderful it was to work with Ron, both on an academic, professional level and on a personal level. And I hope that this is just the beginning of a long-lasting collaboration and friendship. So, and thank you all for being next to me in whatever capacity that you were in the past couple of years. So